Good morning. In today's session, we will discuss about momentum representation and momentum representation of hydrogen atom. Okay, so this is just a theory part. So uh, you just need to read all this. It's not seen asked in question papers. Still, since it is there in the syllabus, I will present it here. Now, what is momentum representation? That is, in advanced dynamics and also in quantum mechanics, linear momentum and spatial position occur on an equal footing. That is, linear momentum as well as the position of a particle both are treated equally in dynamics and in quantum mechanics. Now, here we are going to start spatial distribution first, and from spatial distribution of a particle we derive its corresponding momentum representation. Now suppose that let us consider one-dimensional case first, then we will discuss three-dimensional case. Now let psi of x be a function in one-dimensional space, and this function is said to have the following three properties. First property is that the complex conjugate of the given function into the function dx, that is x of x star, that is this is your function and this is its complex conjugate, into dx. This expression will help you to find the particle in the position between x and x plus dx. That is, that expression is used to discuss about the probability of finding a quantum particle in the position between x and x plus dx. Now, if you integrate this expression from minus infinity to plus infinity, and if you are getting 1 over there, then the particle will be along x-axis, or we say that this is the normalization condition. So this expression gives you the probability of finding the particle in the space between x and x plus dx, and its integral between minus infinity to plus infinity, if that is 1, then it will be the normalization condition. Then this one, this is actually the expectation value in position of the particle x. Okay, that is given by minus infinity to plus infinity chi of star x chi of x dx. So this is how the expectation value in position of the particle is written. Okay, that is, this will give you the average position of the particle along x-axis because it is written dx. Okay, so these three I think you have already studied as the postulates of quantum mechanics, right? First is about the probability density, second one about normalization condition, and the last one about the expectation value or the average value that give you about an idea about the average position of the particle. Okay, that is written here, expectation value. Now suppose that we have a function gp which also gives the same information about linear momentum. That is, p actually stands for momentum. So if gp is a function that give you information about linear momentum, then that function gp will also satisfy the above discussed three properties. See, in place of chi x, here we are writing gp. That is the only difference. This one will give you, as already said, will give you the probability of finding a quantum particle in the momentum between p and p plus dp. In the earlier case, it was actually the probability of finding the particle in a position between x and x plus dx. Okay, because there we were dealing with chi of x position. Here we are dealing with momentum, that is gp, momentum function. So this will give you the probability of finding the particle having momentum between p and p plus dp. On integrating it between minus infinity to plus 1, if you get 1, then that will be the normalization condition, and finally the expectation value. Okay, so if that is the case, that is, if that function gp satisfies the three postulates, then we can represent it as a Fourier transform of chi x as follows. That is this one. This is the relation between the momentum function Gp and the position function chi x. That is Gp equal to 1 by root of 2 pi h cut minus infinity to plus infinity chi of x e raised to minus ip x by h cut dx. Now this will be its complex conjugate. That is, in place of g, you write g star p. This is kept as such. Here you will put a star because it is a complex conjugate. Here the negative sign will become positive. That is the only difference. So that is in the case of one-dimensional case. Okay, that is, this equation represents one-dimensional case. For three-dimensional case, what will happen? This equation. Okay, let us take this equation. This is in the case of one-dimensional case. Now the same equation in three-dimensional case will become like this. That is, this one will become, instead of root, it will be raised to 3 by 2. Integration is kept as such. Then this one, instead of x, that is one-dimensional case. Here you are replacing chi x with chi of r because r stands for x, y, z, 3 dimension. Then e raised to minus ip x by h cut. Here e raised to minus ip r h cut. That is r position vector. R vector stands for x plus y plus z. So 3 dimensional case. Now dx will become d cube r. Okay, that is a volume along x-axis, y-axis and z-axis. That is 3 dimensional space. Okay, so this one is the one-dimensional case and this is a 3-dimensional representation of momentum. Okay, so this is a momentum representation of particle in terms of wave function, that both in one-dimensional case and two-dimensional case. Now let us see the momentum representation in the case of hydrogen atom ground state. Now let chi of r be the 3-dimensional wave function of hydrogen atom in the ground state, and it is given by this expression. This expression you have to study: 1 by pi a0 cube whole raised to half e raised to minus r by a0. A0, you know, it is the Bohr radius given by h cut square by me square. M is mass of electron, E is the charge of electron. Then now the corresponding momentum representation of the hydrogen atom in the ground state will be this one. This equation we have already written. So same equation we are writing it again. Now here what is your x of r? Here everything is written as such. Minus infinity plus infinity is also same. This is also kept as such. Now your x of r is this one. This one, right? So substitute that value of chi of r here. So you will get like this. This is your chi of r. Okay. Now this equation, this one is kept as such. This term, constant term, is taken. Rest everything is kept as such. Okay. Now this equation, this one, this is of the form like this, right? Minus infinity plus infinity e raised to minus ar plus ibr d cube r. Okay, this is of this form. Now for this form, this is the result. So how will this one reduce to? Here in this case, what is your a? Here in this case it is 1 by a0. And what is your b in this case? Minus p by h cut. So remember that and substitute in this formula. That is 8 by a by a square plus b square the whole square. Here as per this equation, compare these two equations. Here in place of a you are having 1 by a0 and in place of b you are having minus p by h cut. So just substitute those values here. That is, these two is kept as such. 8 pi, then what is your a? 1 by a0, it is written here. So a square will be 1 by a0 the whole square. Then what is your b? It is minus p by h cut. Okay, so square it. So it will be p square by h cut square, then the whole square. Okay, then simplify this term. This will reduce to this one. Next, the other two steps are just simplifications. Okay, this one, and then cancel out the common terms and bring it to this form. So this is the momentum wave function of hydrogen atom ground state. So first write about momentum representation in general, and then write about momentum representation of hydrogen atom ground state. Okay, thank you.